So this is the video I'm talking about. So let us watch this all together. So we will have an introduction for our stress topic.
Stress and strain are fundamental concepts that are used to describe how a body responds to external loads. In this video, we'll explore these concepts using the simple example of a loaded bar. Here we have a solid metal bar that is loaded by two equal but opposite forces. We refer to this as uniaxial loading because all of the applied loads are acting along the same axis. The two forces are pulling the bar, causing it to stretch. Internal forces will develop within the bar to resist these applied forces. We can expose these internal forces by making an imaginary cut through the bar. I chose to remove the right side of the bar, but I could have removed the left side instead.
Okay, so we recall our knowledge in section method wherein we are cutting the section and we choose either considering the left zone or the right zone. So you can use the upper drawing here or the lower drawing here. So what is important to apply here is that when we talk on tension, tension is always a force that is always away from the member. So away from the member. So if we are going to cut this and consider the left portion, the internal effect would also be tension. And what is the tension? I have said that it is away from the member. Okay. So by this, we can see now that our illustration, considering the left portion, is in equilibrium because we have two oppositely directed forces. Okay. Likewise, in this one, we cut this into section and then consider the right portion, just the same. This is tension away from the joint, and the internal effect should also be away from the joint or tension. So the opposite of tension is compression, wherein the arrow should be towards the member. Okay?
For any imaginary cut like this one, the internal forces develop in such a way that equilibrium will be maintained. In this case, the effect of the internal forces acting on the cross-section created by our cut will be equal to the effect of the applied external force. I have represented the internal forces as four separate forces here, but I could have represented them as 1 or even 20 forces. In reality, the internal forces are distributed over the entire surface of the cross-section. For this reason, it doesn't make much sense to talk about specific internal forces. Instead, it is better to talk about stress. Stress is a quantity that describes the distribution of internal forces within a body. It makes it easier to discuss the internal state that develops within a body as it responds to externally applied loads. Stress is a measure of the internal force per unit area, and so has units of newtons per meter squared in SI units, and pounds per square inch in US units.
So this is what we call PSI, or pounds per square inch. So this is used in English system. So but most of the time, engineers today prefer to use SI units in Asia. Okay.
Newtons per meter squared are also called pascals. In the case of our axially loaded bar, the internal forces are acting perpendicular to the direction of the cut we made. This type of stress is called normal stress. We can calculate the normal stress in our bar as the applied force F divided by the cross-sectional area A of the bar.
So, as mentioned earlier, these arrowheads could be represented by many arrowheads or a single arrowhead. What is important here in stress is that these arrowheads or force are just distributed to the cross-sectional area. Why is it that cross-sectional area? Because what is being stretched is actually the cross-sectional area. And we said that we have a uniformly distributed, or meaning equally distributed or all over the elements of this whole bar.
It is denoted by the Greek letter sigma. One reason being able to calculate stresses is important is because it allows us to predict when an object will fail. Let's say our bar is made from mild steel, which has a strength of 250 megapascals. The bar will fail when the stress within it exceeds the strength of the material. If our bar has a diameter of 20 millimeters, for example, we can calculate that it will fail if the applied force is larger than 79 kilonewtons.
So the point here is, in every material, there is an allowable sigma. When we exceed that sigma, or meaning if we have an area that is insufficient enough, as we can see here, sigma times area. Area is the determining factor. If we have a small area, the smaller our sigma is. And if we have a larger area, we have a greater resistance. Or meaning, the force will be divided. Parang pag pinaghihati-hatian ng isang force na napakalaki, pag napakaraming hahati, ibig sabihin, liliit yung stress. Pero yung malaking force, inabsorb lang ng isa, dalawa, tatlo, ibig sabihin, may stress siya ng lalo. Okay, meaning, the more the stress. Okay, so that's the concept.
Normal stress can be either tensile or compressive. In this case, the stress is tensile because the forces are stretching the bar. If the forces were trying to shorten the bar, we would have a compressive stress. The sign convention that is normally used is that tensile stresses are positive values and compressive stresses are negative values. In the case of our bar, it is reasonable to assume that the stresses are distributed uniformly across the cross-section and along the length of the bar. But this is a very simple scenario. The stress distribution in a beam that is bending, for example, will be more complex. Stresses will be tensile on one side of the cross-section, but compressive on the other.
So why is it that the top portion is compressive? As we can see here, the top portion was compressed actually. And beyond this line, at the bottom, it is stretched, or the I-beam was lengthened. So the boundary between them is what we call the neutral axis. In the neutral axis, the stress here is equal to 0 because this is the transition. At the below the neutral axis line is the tensile, and the upper portion beyond the neutral axis on the upper hand is compressive. But if we have a bending that is concaving downwards, this will reverse.